Hello and welcome to the mathematics class. Today our topic will be surface area and volumes. We need to find the surface area volume of a three-dimensional figures, and for that we already know we have certain type of 3D, that is three-dimensional figures like the cube or a cuboid. This is the cube where we have the arrangement of 6 rectangles. You can see these are the 6 squares in case of cube, and in case of cuboid there will be 6 rectangles. These are called the faces of the cube or cuboid, and you can see there are 4 surfaces along side to side and 2 surfaces from top and bottom. So in all we have 6 surfaces for cube and cuboid. For cube we have 6 square surfaces, and for cuboid we have 6 rectangular surfaces. And the next one is the cylinder. It has 3 faces. You can see one is the curved face, one is the curved face of the cylinder, and another are the circular faces, the top and the bottom. So this is the cylinder. And next we have the cone, which has a triangular face, if you see from one view, and a circular base. This is a cone, and in a cone only 2 faces are to be considered. One at the bottom base, that is the circular, and another is the triangular face. This is the cone. And the next one is the sphere, which is round 3-dimensional figure. This is the sphere you can see, and the half of the sphere is the hemisphere. So in class 9th we were able to find the total surface area, the curved surface area, and the volume of all these 3-dimensional figures we are dealing with, and the same surfaces are to be dealt in class 10th also. Now the formulas for finding the surface area and the volume remains the same, but in class 10th we are having such type of problems where we are given 2 or more than 2 3-dimensional figures combined in a single solid. Suppose we take a cube or a cuboid, and while drawing this on the board, we see that for a cuboid we have rectangular surfaces, and for a sphere or hemisphere we need to draw a half circle with the top circular base. This is the hemisphere. Now if we find the surface area of the combined figures, we need to understand how the surface of that solid will form. Suppose we are given a question that a vessel is in the form of a hollow hemisphere. Now this is the hollow hemisphere, hollow from inside, and it has a circular base mounted by a hollow cylinder. Now we take this as a hollow cylinder and it is mounted on that. That means one of the surface of the cylinder is almost covered by the sphere, and the figure becomes like this. Then we are given that the diameter of the hemisphere is 14 centimeter because it is exactly mounted on the cylinder. So we take the diameter of the cylinder equal to 14 centimeter as well. And the total height of the vessel, if we consider this as a vessel, the total height is the height of the cylindrical part and the height of the hemispherical part. The height and the radius of the hemisphere always remains the same. So for the height for the whole this vessel remains the height of the cylindrical part plus the radius or the height of the hemispherical part, gives the total height of the vessel. Now the total height of the vessel is given 13 centimeters. We have to find the inner surface area of the vessel. What is the inner surface area of the vessel? If we ignore the thickness of this type of solid, the inner surface area will be equal to the outer surface area. How can we find the inner surface area of this vessel? It's simple. We consider the inner surface area of the cylinder that we already know is 2 pi RH, and the curved surface area which is exposed to the outside. This you can see, this is the cylindrical part whose only curved surface area is exposed. We need to find the curved surface area of the cylinder and the curved surface area of the hemisphere. On adding both these areas, we will get the total surface area of the vessel. This is how this question is done. Now, if we make this figure, same figure on the board, it will be like this. First, a vessel is in the form of a hollow hemisphere mounted by a hollow cylinder. This we draw a hemisphere. And on that we mount a hollow cylinder. This we consider the height of the cylinder, and the height of the cylindrical part the diameter of the hemisphere is 14 centimeter, and the total height of the vessel. The total height of the vessel is the height of the cylindrical part and the height, or you can say the radius of the hemispherical part. This is the cylindrical part. On adding the hemispherical part, the total height of the vessel becomes 13 centimeter. Now, if the diameter of the cylindrical part or hemispherical part is 14 centimeter, then its radius is 7 centimeter. And for hemisphere, the height or the radius remains the same, because you know the center of the sphere or hemisphere lies inside the center of that three-dimensional figure. So, from all the sides, the radius of the hemisphere will be 7 centimeter. If you subtract this radius of 7 centimeter of hemisphere with the whole height, you will get the height of the cylindrical part. So, we can write it as radius of cylinder will be equal to radius of hemisphere and for both the radii we denote it by small r and write it as 14 divided by 2, that is 7 centimeter. Now the height of the vessel is 13 centimeter. The height of this cylinder and the height of the hemisphere together gives the height of the vessel. In order to get the height of the cylindrical part or cylindrical portion, which we denote by small h, will be the total height of the vessel subtracted by the height of the hemispherical part, and the height of the cylinder is 6 centimeter. This is exactly like this shape. You can see the height of the vessel in all is 13 centimeter. The radius or the diameter of hemisphere and cylinder remains the same. So, from the whole vessel, if we subtract the radius of the hemisphere, you will get the height of the cylinder. So, to find the total surface area of the vessel, we need to find the curved surface area of the cylinder. CSA, curved surface area of cylindrical part, plus curved surface area of hemisphere. We know that the curved surface area of cylinder is 2 pi r and h, and curved surface area of hemisphere is 2 pi r square. Now, between the two, 2 pi r is common, and within the brackets remains h and 1 r from 2 pi r square. When we insert values for all these parameters of radius and height, we get 2. For pi, you write 22 by 7. For radius, you write 7. For height, it is 6, and radius again 7. So 7 and 7 is cancelled. 2 into 22 is 44, into 6 plus 7 is 13. Now 44 into 13 is 572. So the total surface area of the vessel formed is 572 centimeters square. A toy is in form of a cone of radius 3.5 centimeter mounted on a hemisphere of same radius. Now, how can this figure be formed? A conical part is mounted on hemisphere. So, let us draw hemisphere, and then we can mount a conical part on that. This is the shape of the toy. The radius of the cone and the height and the radius of the hemisphere remain same, that is 3.5 centimeters. The total height of the toy is 15.5 centimeter. This is the total height of the toy, 15.5 centimeters. Now, we are told to find the total surface area of the toy. Now, we need to understand and imagine how this figure forms. Suppose we take a hemisphere, the half of the sphere with a curved surface and a circular base, it's hollow. And then we take another figure of toy, that is cone portion, we take another cone portion. And when the question says a toy is in the form of a cone mounted on a hemisphere. This is cone, you can see a hollow cone, and this is hemisphere. The cone is mounted on a hemisphere. The radius of the cone and the hemisphere remains the same, and the toy exactly looks like this. We need to find the surface area of that toy. You can see the exposed surfaces of the toy, and you can yourself deduce its surface area. Now, understand how much and what sort of surfaces are exposed. You can see the curved surface area of the cone is exposed. We do not need to do anything with its base, and the curved surface area of the hemisphere is exposed. To find the total surface area of that toy, we need to find the curved surface area of the toy, the curved surface area of the conical part, and the curved surface area of the hemispherical part. Now, one thing we need to understand is that curved surface area of cone is pi r L, where L happens to be the slant height, and the curved surface area of hemisphere is 2 pi r square. Now, what we are missing actually? We are missing the slant height of the cone. This is missing. The slant height of the cone is not given. and we need the slant height in order to find the curved surface area of the cone. How can this be done? Because that portion, the height and the slant height with the radius, forms a right triangle, and we apply Pythagoras theorem to find the slant height. So in order to find the slant height for cone, we need to use this type of formula, that is r square root of r square plus h square. Now we are left with the height of the cone that is not given. So how can we approach this question? This is the third question for exercise 31 of your textbook. How is height to be found? Now, height of the cone or conical part can be denoted by small h, and it will be equal to the total height of the toy, that is 15.5 centimeters, and we subtract the height of the hemispherical part. Again, the radius and the height for the sphere remains always same, or hemisphere or sphere remains the same. So if we take 3.5 centimeter, the radius of the hemisphere, then height in this case for the hemispherical portion will be the same 3.5 centimeters. Now you subtract 15.5 with 3.5, you get 12. So alone, the height of the conical part is 12 centimeters. Now, let us denote the slant height of the toy or conical part by L of conical part be L centimeters. In order to find the slant height, we need to calculate the radius square and the height square with a square root. The radius is 3.5 whole square, and the height is 12 whole square. It becomes 12.25 and 144. In order to make yourself sure, always do manual calculations. It's 12.25, and when 12.25 is added with 144, you get 156.25. Square root of 156.25 is 12.5 centimeters. Now we need to find the total surface area of the toy. How can we find that? The curved surface area of the conical portion and the curved surface area of the hemispherical portion is to be added, and this way we will get the total surface area of the toy. So total surface area of the toy is the curved surface area of conical part added with the curved surface area of the hemispherical part. Now the curved surface area of conical part is pi r L, and the curved surface area of hemispherical part is 2 pi r square. Now between the two, pi r is common, and within the brackets remains those who are not common. It's 2 and 1 r from 2 pi r square. Now we can insert the numerical values for each. Pi is 22 by 7. R is 3.5, you can write 35 by 10. L, we got 12.5. And 2 into R is 3.5. 7175, 5152, 21 to 11. 11 into 12.5 plus 7, that's 11 into 19.5. 11 multiplied by 19.5 gives 214.5 centimeters square. This is how the answer is obtained. So, the total surface area of the toy that was mentioned in the question is 214.5 centimeters square. Another question from the text we are given is that there is a cubical block like this. There is a cubical block. The side or the edge of the cubical block is 7 centimeters. And it is surmounted by a hemisphere like this, and the figure forms like that. A cubical surface with 6 square surfaces and a hemisphere mounted on that. We imagine that it is stuck to one of its surfaces, and the figure looks exactly like this. Now the question is, what is the greatest diameter of the hemisphere we can have? And simply we can find, if the hemisphere is completely mounted on that cubical surface, the edge of the cube and the diameter of the hemisphere remains the same. If we are given the edge or the side of the cube is 7 centimeter, it means that the diameter of the hemisphere, which is completely mounted on that hemisphere, will also have diameter equal to 7 centimeters. Now, what do we need to find? Find the total surface area of the solid so formed. Now, because we know the total surface area of the cube or cubical figure or solid is 6 edge square. Now, if we mount a hemisphere on this, imagine that 5 surfaces you can easily find. Now, the 6th surface needs some sort of attention. You can see the corner parts of the cube are still exposed, and the rest of this surface of the top face gets imposed by the hemisphere. Now, what is the area that is lying inside the base of the hemisphere? We know the base of the hemisphere is exactly similar to the circle, and it will cover the area of the cube exactly equal to the area of the circle, and the area of the circle is the area of the base of the hemisphere. Now, when we put this hemisphere on the edge or the face of the cube, you can see only corner parts of the cube are exposed. So, what will be the total surface area of that solid? We can find the 5 surfaces of the cube. The 6th surface needs some sort of arrangement, some sort of deductions. That is, first we take it as the whole surface, the 6th surface, and we subtract the circular surface from it because it is not exposed, it remains under the base of the hemisphere. Now, if you subtract all this, you will get the corners of the 6th surface that are exposed. and with that we add the curved surface area of the hemisphere. So this solid exactly looks like this. If we draw the sixth face on the board, on your blackboard, it is the top view of that solid, and this is the circular base that gets covered under the hemisphere. Only this portion is exposed. Now, how can you get the area of the shaded region? That is the top of that solid, this solid. So, if the side of the solid is 7 centimeters, then the diameter of the hemisphere is also 7 centimeters. So when you subtract the area of the circle from the area of the square, you get the area of the shaded portions. This way, you get the total surface for the cubical solid only. And now the hemisphere is mounted on that. You need to find the curved surface area of the hemisphere. So on adding that, you will get what the question asks. So how can we approach that question? The figure looks just like this. This is a cube. And a hemisphere is mounted on that, like this. So, from the 6 surfaces of the cube, we need to subtract the surface of the circular base and then add the curved surface area of the hemisphere. So, edge of the cube is 7 centimeters, then diameter of hemisphere is also 7 centimeters. Or we can say the radius of hemispherical portion is 7 by 2, that is 3.5 centimeters. In order to make this question easy to write, we write straight away the total surface area of the solid formed. So you can write, first consider only the cubical part with its total surface area of cubical part. Add the curved surface area of the hemispherical part. And we need to subtract the base that comes under the hemispherical part. Area of base of hemisphere, because it is circular in nature. So, to sum up all this, if we denote the edge of the cube by L, and we can write the total surface area of cubical part is 6L square. The curved surface area of the hemisphere part is 2 pi r square minus the area of the base of hemisphere, that is circular in form, and the area of circle is pi r square. And this all becomes 6L square, the edge of the square, and pi r square. On inserting numerical values, radius is 3.5, we can write 35 by 10. Now on cancelling this, 5 sevens are 5 twos are. So it is the total surface area of solid is equal to 6 into 7 square is 49, 11 into 7, 77 upon 2. So 6 into 49 is 494, and 77 while divided by 2 is 38.5. It is 332.5 centimeters square.